This screen is going to be covering the subject of how the reactants actually rearrange when they collide and form the products. So what we're looking at is what happens during this part of the chemical reaction and how those collisions take place. What that's called is the mechanism. So it's the mechanism by which the atoms collide, break bonds, form new bonds in order to rearrange to become the products. So the reaction that we're going to be working with is this one. It's H2 plus 2ICl goes to 2HCl and I2. So if we look at possible mechanisms, one of the possible mechanisms we could have would be to have one hydrogen gas molecule and two ICl molecules come together at the same time, collide and go to products. That would be what we call a one-step or unimolecular step in the elementary process, or an elementary step in the mechanism. And there's only one elementary step here. And we would have to have, here's your ICl, one ICl here, you have another ICl here, and here's your H2. And all three of these would have to come together at exactly the right angle, so line up something like this, so that the H2 bond can break, so the ICl bonds can break, so that the I2 can form and these two HCl's can form all at the same time, at that same instant. So the probabilities here are quite large. Three things have to come together. They have to come together at the right angle and location, and they have to have the right energy. So that's really difficult. And so most reactions don't happen like that, where we have three reactants that need to all show up at the same place at the same time. So this is one possibility, although it's not a very probable possibility. It is a possibility. This has two elementary steps. One of them is slower, one of them is faster. In the first one of the H2s and one of the ICLs come together. You make HI, and then you make HCl. So there's one of my products. There's HCl. And this is a slow step. Keep that in mind. I'll show you what that has to do with this diagram in a minute. Then that HI comes down here. It's used up in the next reaction, and it reacts with the ICl, makes another HCl in the I2. So a couple of things. First of all, this HI was made, but then it's used up. Because it's made and used up, it's something called an intermediate. Then, if I add up everything that remains, I do get the overall reaction. H2, there's the two ICLs, here's my two HCLs, and there's the I2. So it does work. These two that were made and then used up are called intermediates. An intermediate is just that. It's something that is made in the reaction but is used up. So that's an intermediate. Now, let's explain this slow step. Look at your potential energy diagram. Instead of this potential energy diagram just having one curve, it actually has two, one for each of the steps. So you don't see this detail, or haven't seen this detail up until now. It corresponds to the slow step because look at this activation energy. This activation energy here is so much higher than the second activation energy. And so because it's slow, it must have a higher activation energy. And that is going to be called the rate determining step, which you'll see on a slide in a couple of minutes. Rate determining step. Okay. Here's another possible mechanism, and this one looks at a four-step, or there's four elementary steps. Again, one is slow, and the others go really, really fast. If you take a look at this, the H2 and the ICl have to come together in the first part of this reaction, and that has the highest activation energy, and that's why it's considered the slow step. Now, I can only go as fast as my slow step. So if I increase the hydrogen and the ICl, according to this, they both should increase the rate of the reaction. Now, when I go and look at this, what I want you to do is put the screencast on pause for a second, and I want you to identify any intermediates that might exist here. So pause it and then come back, and we'll see if you've identified them correctly. All right, so you should have had HCl as an intermediate, H's as an intermediate, and then there's one more. The I's are intermediate. When you add up everything that remains, you still get the same overall reaction, just a lot more intermediates in this. You would normally see the potential energy diagram written like this. You wouldn't see all the detail underneath, but there is often a lot of detail that you don't see. So rate determining step, only the compounds that are found in the slow step are expressed in the rate law. So if I take a look at this reaction, A, B, and C combine to make F and G. So notice my rate law. My rate law is rate equals K. I've already figured out it's A to the first, B to the second, and C to the zero. What that means is that C, since I increase the rate and increase the concentration, it doesn't change the rate, it must not be part of the slow step because you can only go as fast as your slowest step. If you want to increase the rate of your reaction, you have to work on increasing the collisions in the slow step so that the reaction can go faster. So if I were to look at this and figure out what is present in the slow step, I would know that there would be 1A plus 2B's in the slow step of the reaction as reactants. Slow step reactants. So whatever the order is, that's how many of that component are present in or as reactants in the slow step of the reaction mechanism. So write the rate law for each of the proposed mechanisms below. So if this was only a one step, what would the rate law be? Well, you go back. If it's only one step, it also has to be the slow step. So you had 2 ICLs and 1 H2. So rate equals K times the concentration of ICl to the second, and then H2 to the first, because there's only one of them. In this mechanism, your slow step has these two reactants, and then you write your rate. Rate equals K, concentration of H2 times the concentration of the ICl. There's only one, so you get a 1 for the order and 1 for the order for the H2. One more. This has the same reactants, so it would have the same rate law. There's one H2, there's one ICl, and remember, we only put what's in this, the reactants in the slow step, into the rate law. So write the overall reaction defined by the mechanism below. I'm going to give you a second to write it. The N2O2s, remember, are intermediates. So if I cancel those out, I end up with 2NO plus O2 goes to 2NO2. And what's the purpose of the N2O5? Well, I think I have it in there. It's an intermediate. It's made and then it's used up. One more reaction here. Write the overall reaction defined by the mechanism below. And this one's a little different. When I go to add this one up, I make AB and I use it up. But B is in the beginning and then it's spit out again at the end. That's a little different. So the purpose of B is that B is a catalyst. It is not an intermediate. The difference is that AB is made and then used up, so it never sees the beginning or the end of the reaction. When I go to finish and write the overall reaction here, I get A plus B plus C goes to AC plus B. Now you'll notice that I have B's on both sides. That's the presence of the catalyst. Another way that you can write the reaction is to do A plus C plus B, which your catalyst could go over your arrow, goes to AC. And that's it. That's a wrap. I'll see you tomorrow. Have a good night.